For any civil engineering project, it is necessary to plan an appropriate soil investigation program. Investigation of underground conditions at the site is an essential prerequisite for economy in design and construction of foundation for any engineering structure. The principal objective of soil investigation is to assess the properties and behavior of soil as an engineering material. There are many techniques and methods of soil investigation. These are boring, pit sampling, drilling, and geophysical methods. One of the major techniques to measure the strength characteristics of soil is by determining its resistance to penetration. A commonly used and relatively economical method is standard penetration test. In this test, a standard sampler is driven into the soil by the impact of a falling hammer to determine the penetration resistance of the soil. Let us now see the equipment and procedure for conducting the standard penetration test. The location where the test has to be conducted is marked on the ground. A borehole of about 100 to 150 millimeter dia is made up to the depth where the test has to be carried out. This is how the test setup looks like when assembled. Two legs of the tripod consists of hollow pipes and the third is solid section. First of all, the tripod is to be fixed. Ensure that nuts are fastened tightly so that when erected, the tripod is stable. These nuts are fastened partially so as to keep these joints flexible. A thick and strong rope with an iron hook on one end is passed over the pulley. The tripod is thus ready for its erection. The tripod is erected by lifting it manually, giving adequate support from all sides. The tripod is centered by adjusting the legs so that the hook suspended from pulley is over the bore hole. All the legs are firmly anchored to the ground by means of arrows. The split spoon sampler used for penetration in this test has outside diameter of 50.8 millimeter and inside diameter of 35 millimeters. The sampler is cleaned and assembled. check that it does not have a damaged drive shoe. The sampler head is now connected to the A rod using a coupling in between. The sampler is then lowered to the bore hole. To keep the drive rod vertical, a centric guide is inserted and fixed on the ground. Marks at heights 15, 30 and 45 centimeters above the centric guide are made on the drive rod. A guide rod having a mark 75 centimeters above the driving head is connected through the drill rod using a coupling. The rope is lowered and the hammer chain is hooked to it. The hammer has a mass of 63.5 kilograms. The hammer is raised up to 75 centimeters mark, allow it to fall freely. In this manner, the sampler is driven into the soil, but number of blows for first 15 centimeter penetration are not recorded. Driving is continued for next 30 centimeter penetration, and the number of blows for each 15 centimeter penetration are counted. The total number of blows is known as the observed N value. For taking out the sampler, blows are imparted in reverse direction. open the sampler and visually examine the soil sample. Observations based on visual examination are recorded in a performer. Note that the sample obtained from the test is a disturbed sample. The soil sample can also be used for relevant laboratory tests. The test is suitable for sandy soils which do not have gravels or rocky stratum. If the number of blows for any 15 centimeter penetration exceeds 50, the test should be discontinued and it is recorded as refusal. Discrepancies in the test result may be caused due to using a worn or blunted shoe, a rock or stone piece coming directly below the cutting edge, using a liner inside the sampler. The N value obtained from the field is corrected for overburden pressure and water table. N value for cohesionless soils is corrected for overburden effect by N dash is equal to Cn into N. The correction factor Cn is found from the chart shown. The second correction is applied for dilatancy if the stratum consists of fine sand and silt below water table. For values of N greater than 15, the corrected value is obtained as by this equation. Extensive experience have enabled to establish empirical relationship of N value with various soil characteristics. For cohesive soils, with the knowledge of N value, it is possible to have an idea of unconfined compressive strength and consistency. For granular soils based upon the N value, various parameters like relative density, angle of shearing resistance, etc. can be estimated. This graph shows how the value of angle of shearing resistance phi is related with N value. Knowing values of phi, the values of bearing capacity factors Nc, Nq, and gamma obtained from the graph, and using this equation, net safe bearing capacity against shear failure can be estimated. It is also possible to estimate the net foundation loading intensity for a given permissible settlement. The lesser of these two values is the desired allowable bearing capacity and is used for foundation design. From same graph, the probable settlement of footings for different foundation loading intensity can be obtained. The N value is also useful to determine the bearing capacity in case of piles. Though N value has many applications, it should be used cautiously in dense saturated fine sand and silts and highly sensitive clays. Now let us summarize. In standard penetration test, the number of blows required for 30 centimeter penetration of a standard sampler by a freely falling hammer of standard weight is noted. Knowing the N value, we can obtain information about various soil characteristics like shear strength, consistency, relative density, unconfined compressive strength, etc. This information is quite useful for design of foundations.